Alright, so this is going to be part 3 of integral test practice. Okay, so we want to prove that the series n equals 1 to, the sum of n equals 1 to infinity of 1 over n squared plus 9 is convergent or divergent. Okay, so the first thing that we need to do, of course, as always, is use the test for divergence. So you take the limit as n approaches infinity of 1 over n squared plus 9, and you can see that, of course, this is just going to become infinitely large on the bottom, so we get that this limit is equal to 0. Okay? So that means that the test for divergence is going to tell us absolutely nothing. Now, what we need to do next is we can compare this series to a function, okay? And we just basically plug in our x for our n, okay? And we get 1 over x squared plus 9. Cool. And we want to use this function from 1 to infinity. Okay, that's always the good starting point. 1 to infinity. Now, to be able to use that, we need to see if this is continuous, positive, and decreasing along that interval. So first, is it continuous? Well, the only way this would be a discontinuity is if this x squared somehow could be a negative 9, and we know that that can't happen, so this would have to be continuous. Now next we need to see if it's always going to be positive, and since we have an x squared here and everything else is positive, of course that x squared is only going to give us positive values, so we know that this whole thing is always positive. Now is it decreasing? Well, as x gets bigger and bigger, this denominator becomes bigger and bigger as well, so this whole fraction becomes smaller and smaller. This is in fact decreasing. Okay, so now that we've identified that it's continuous, positive, and decreasing, we can actually take our integral from 1 to infinity. Alright, so if we want to do that, we can take the limit for as t approaches infinity, the integral from 1 to t of 1 over x squared plus 9 dx. Okay, and now what does this look like to you? Well, we have that x squared plus 9 in the denominator. We don't have an x in the numerator or anything like that where we can do an easy u substitution. So you can see that this is an inverse trig substitution. Okay, and that means that we're going to have to do x equals, well, this is a tangent case, okay, because we have x plus a number, okay, so we have x equals this, well, kind of like the square root of this, I guess you could say, x equals 3 tangent theta, okay, and that means that dx is going to equal 3 secant squared theta d theta. Alright, and now we need to figure out our bounds. So when we had that x equals 1, well, if we have a 1 here, okay, we have 1 equals 3 tangent theta, well, that means that theta equals tangent inverse of 1/3, which we're not really too sure what that is, but you're going to see later on that that doesn't actually matter. Okay? When x equals t, well, that's just going to be, well, basically you get that theta equals the tangent inverse of t over 3. But as t approaches infinity, okay, this number is still going to become infinitely large even though it's being divided by 3. So we can basically just say that this is the same thing as tangent inverse of t, and, well, that's just going to be pi over 2. Alright, that's what we know about that tangent inverse graph. So we know that theta is going to equal pi over 2. Okay, so now we have our new set of bounds and we have our substitutions, so now we're all good to go. Okay, so making our substitutions here, we get that the limit as t approaches infinity of the integral of tangent inverse of pi over, not pi, 1 over 3 to pi over 2, and we have our integrand, which is now going to be 1 over x squared, that's going to be this squared, which is 9 tangent squared theta, and we add 9. Okay, and our dx, don't forget that, that's 3 secant squared theta d theta. Cool. Now, we can take out a 9 out of the bottom here. We can take out this 3 on top. So we end up with just getting the limit as t approaches infinity of 1/3 the integral of, when we have our bounds here, tangent inverse of 1/3 and pi over 2. And we now have a secant squared theta over a tangent squared theta plus 1. And of course we have d theta here. Okay, now tangent squared theta plus 1, we know that's secant squared theta. Okay, and we have a secant squared theta on the top too. So this will actually just become 1. So this just goes down to the limit as t approaches infinity of 1/3 the integral from tangent inverse of 1/3 to pi over 2 of d theta. Okay, which is actually really nice considering what we started out with. Okay, now all we have to do is just do our integral right here. We get the limit as t approaches infinity of 1/3 times theta, evaluated from the inverse tangent of 1/3 to pi over 2. Okay, and now we can just plug that in our evaluation step. We get the limit as t approaches infinity of 1/3 times times pi over 2 minus the inverse tangent of 1/3. Okay, and this number is a finite value. Okay, it's a finite value, so we know that this is going to be convergent. Okay, because these are all finite values. So since this integral is convergent, we know that by the integral test, our series is going to be convergent as well. All right, so it didn't really matter the exact number that tangent inverse of 1/3 was, okay? We know that's going to be a finite value. So to be honest, it doesn't matter at all. All right, just as long as we know that it's a finite value, we can say without a doubt that this is convergent. So by the integral test, our series is convergent. And that's going to do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series, the explanation video for the integral test, and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.